last-minute technical difficulties, and we're finally done. So we have a session full of papers, 5 papers on video and SIGCOMM. I'm very glad to have those papers. The first one, the first presenter is Lian Chen Jia. He is currently a PhD student at Tsinghua University. His research interests include adaptive streaming, congestion control, and machine learning systems. He'll graduate in this December and is actively seeking job opportunities. So with that, please welcome Lian Chen.
Okay. Hello, everyone. I'm Lian Chen Jia from Tsinghua University. It's my honor to introduce our work towards user-level QoE, large-scale practice in personalized automation of adaptive video streaming. As we all know, video streaming is no longer just an application. It dominates the internet. Recent industrial reports show that traffic constantly makes up the largest portion of all internet traffic, and it continues to grow at a high speed. This means the video streaming has evolved into an internet service infrastructure. This picture shows a simplified view of a modern adaptive video streaming system. On the server side, a raw video is encoded into multi-quality versions. On the client side, the ABI algorithm makes the key decisions. It monitors the network and the player buffer to select the most quality of the next video segment. The ultimate goal is to provide the best possible quality of experience, or QoE. In research, we often measure this using 3 QoS metrics: video quality, rebuffering, and video smoothness. ABR technologies have been developed for over 10 years. So the question is, in 2025, after over 10 years of development, how much room for optimization does video streaming still have? Last year at InfoComm, we presented our work on closing the sim-to-real gap with a gap between our simulator and the production environment using offline reinforcement learning. This work achieved good results, but it also revealed some interesting remaining issues. We modified the optimized objective of the online heuristic algorithm to favor error low stalling or high video quality. From the perspective of QoS metric and the linear QoE metric, this algorithm can achieve corresponding improvements. However, for the QoE metric that the industrial care about most, user watch time, it is difficult to achieve significant improvement. It maybe means that improve traditional QoS metric is difficult to translate into the growth in the production environment, QoE metric, user watch time. Why is this happening? Because for the vast majority of users, the system is already highly optimized. Over 19% of our users experience zero stall in a single day, and less than 10% of users have an average bandwidth that is lower than what the highest video quality requires. This means that system-wide, one-size-fits-all optimization has no point of distinguished returns. So, what should our new optimization target be? The most direct metric is watch time, but watch time is a very long-term metric. The feedback is too slow to guide real-time decisions like adaptive video streaming, which happen in seconds. We need a more sensitive, fine-grained metric. This metric is user exit rate. We can observe if a user exists at the level of each segment, which gives us an automatic signal about how they feel. We analyzed mailing-level real user records to validate this. Just as figure A, to summarize what we found, the impact of video quality is on the order of 1,000. the impact of battery switch is on the order of 1%, but the impact of stalling is on the order of 1/10. Which is massive, it's far greater than the order two combined. Our first finding is stalling as the most important significant factor includes the QoE. Even more interesting, we found that different users have very different tolerance for stalling. The difference in stall tolerance between users is significant, as figure A. And for the same user, its tolerance is quite stable over 2 days. Here are a few real cases. Some users are sensitive, some are not, and some sensitive to specific thresholds. Our second takeaway is this stable individual difference are the foundation that allow us to shift from system level to user level personalized optimization. Based on this finding, we designed and implemented the 0C system, which is the first large-scale deployed adaptive video streaming system in the industrial towards user-level personalized QoE. We call it 0C from a Chinese poem for being on the same wavelength, because the algorithm is designed to intuitively connect with each user's unique feeling about QoE. 0C is not a brand new ABI algorithm. Instead, think of this as an automation module that works together with any existing ABI algorithm. Its goal is to personalize the ABI strategy for its user. While the user is watching a video, 0C is triggered when the automation process begins. The first challenge is how can we continuously optimize for every single user? Our solution is online-based optimization. You can think of this. Contact individual online-based optimization for its user. Start from current parameter each time. The second challenge is ABI algorithm decision has both a immediate and long-term impact on QoE. Our solution is Monte Carlo sampling, generate virtual platform choices to align the immediate and long-term on the different parameters. After this, we can use online-based optimization to generate parameter counters and give this parameter counter to simulate the environment and using Monte Carlo sampling to generate some virtual play trace. And after get this virtual play trace, we can use exit rate predictor to give the final prediction exact rate. We use a hybrid exit rate predictor that combine an overall statistical model of video quality and video smoothness with a personalized model focused specifically on stalls. So in this way, we can transfer from parameter counter from an ABI algorithm to a virtual play trace, and finally, we can get the QoE metric aggregate rate. After getting aggregate rate, we can use Bayes optimization to select the lowest aggregate rate current to the parameter counters. And we use these parameter counters to deploy it on the player. So this is the workflow of 0C work. The personalized prediction uses both short-term states, such as recent bit rate, and long-term user behavior, such as stall and reaction history, to predict the probability of existing. To build a personalized model, we need enough data, but most users rarely experience stalls. This is a trade-off. Our strategy is to active personalized optimization for users only after they have experienced more than 2 stalls. we run a large-scale A/B test on the Kuaishou application for over 10 days, covering 80% of our total traffic. On QoE metric, we saw a 0.15% increase in total user watch time. Well, it maybe seems a very tiny improvement, but for a platform with hundreds of millions of daily users, this is a huge improvement, equivalently to the watch time of 45,000 new daily active users. On QoS metric, we also saw a 0.5% higher average bit rate and a 1.3% reduction in total stall time. This shows that by better understanding user, Lingxi achieved improvement in both QoE and QoS. The 0.15% is an average improvement. Lingxi's real value is helping the long-tail users who have poor network conditions, such as left figure. Lingxi automatically adjusts the parameters for users with different bandwidth. It's more conservative in low bandwidth and more aggressive in high bandwidth. The effect is clear. In low bandwidth situation below 2000 kbps, Lingxi reduces stall time by up to 15%. This proves that Lingxi puts optimization resources where they are needed most. To further show whether Lingxi truly understands user personalized performance, we conduct more detailed user-level analysis. We can see that the data from each day shows a clear negative correlation trend line. It means that for users who are very sensitive to stalls and exist immediately when stalling occurs, Lingxi assigns them lower, more conservative parameters to minimize stall as much as possible. Conversely, for users with high stall tolerance, Lingxi assigns more aggressive parameters. Let's look at a few real user cases to express Lingxi dynamic adjust process. User 1 and 2 are tolerant users. They got aggressive parameters to maximize quality, even with occasionally stalls. Users 3 and 4 are sensitive users. They got conservative parameters and dynamically lower in response to exit. This shows Lingxi's ability to make both stable long-term classifier user and rapid short-term adjustment. To summarize our main contribution, we revealed a new direction. Our analysis of millions of real users so that system-wide QoS optimization reached its limits. The future of personalized optimization. We designed a new system. We designed and deployed Lingxi, the industrial first large-scale user-level personalized video streaming system. It uses a hybrid exit rate model to dynamically match each user response to stalls. We deployed it on the production environment, and Lingxi achieved both improvement in QoS and QoE, and specifically for some people who in weak network conditions. Okay, that's my presentation. And last but maybe most important thing that I will graduate, and I'm looking for any post-operation or research opportunity. If you have any chance, you can connect me. Okay, I think I'm finished. So any question?
Question?
Thank you very much for the great talk. One question, in your model, what is your prediction objective? Is that the watch time or is that the stall? Because you did mention some users sensitive to stalls, some don't, right? If that's the case, it seems to me the prediction objective should be watch time. But one of your slides mentioned Lingxi actually improved the stall. So I was a bit confused. I thought Lingxi should improve watch time.
Okay, I still can. Well, that's a very good question. Well, I guess watch time is the most important metric, but sadly we found that watch time need a lot of time to maybe collection, and it's very hard to reflect a sensitive fine-tune metric. So maybe we should to use exit rate, not the watch time. And maybe, yes, some people may sensitive to star and some not. And we use the history of the, maybe this one, they use some of this history reaction. Maybe some people meet a star and they exit, and some people meet a star, they don't. So we use this to predict they will exit or not, and we don't predict the watch time. Thank you.
Yes. Okay. Thank you very much. Very interesting talk. I was wondering about the scalability of this system. Like, what happens if we have a very large number of users concurrently trying to optimize their experience with Ling-Shi? Have you done tests into how scalable this is, how much it impacts the server?
So your question is how we put this system online in DICE or other platform?
Yes.
Well, we deploy it on Kuaishou, a Chinese company. And, well, I guess it's very similar with DICE system. And I guess if we use DICE system, we can also use this system on the DICE.
Okay, thank you.
Thank you for your talk. My question is about the implementation and the way that you collected the results. Is based on subjective tests or just analytical, measurement?
Sorry, I don't hear from you.
Yeah, I ask about the way that you collected the results. Is based on the subjective test with the group of people involved with the test and measurement, or just based on some for example, analytical measurements?
You want to ask the result? This one?
As far as I know, it's based on the service, what you observe from the service of the actual users. Real users, yeah, right?
Okay, thank you.
Yeah, one final question.
Wait, do we? Yeah, well, actually, it's maybe related to what Farzad asked, because usually quality of experience, kind of subjective overall notion of satisfaction of the user, and you seem to be looking at objective metric of watch time or engagement. But engagement doesn't really directly correlate with QoE, right? Because people can be watching the video for longer because they're interested in the content, not how good the AB algorithm is working, right?
Yes. I think that the content is very important aspect. But in this work, we don't analyze the influence and content. We use another way. We have a lot of users, and I guess maybe we can consider it that random experience. Some people use some same content and some don't some content. So we use very large user to try to reduce the influence of content. But I think if we consider the content influence, we can make this work better.
I mean, very quick question, just push back about your results. You said that 0.15% is really important in practical system, but I really doubt, like the rule of thumb in the real world, if it's less than 1%, it doesn't really matter. So, I kind of respectfully disagree that this improvement of 0.15% is really meaningful.
Okay. Well, for a production environment, the improvement is very large. We have do this work many years. So the last people may have make this system nearly perfect. So the improvement in a metro production environment, very little improvement is important. And another point is that maybe this is only 0.15%, but we consider the DAU, daily active user. It means that we add 45,000 daily active user. If we use this way, it shows, wow, this may be a very great improvement.
Okay, yeah, in the interest of time, we have to move to the next speaker. So let's thank the speaker. Thank you.